Welcome to this explainer. Today, we're diving into something that is literally going to break your brain a little bit, but in the best way possible. We're going to explore exactly why the everyday common sense logic that we rely on completely shatters when we zoom all the way down to the atomic building blocks of our universe. Because as it turns out, reality just doesn't operate the way our eyes tell us it does.
Okay, so let's just start off with a surprisingly simple question. Based on the classical laws of physics, the stuff we experience every single day, how long can an atom actually exist before destroying itself? Just think about the fundamental rules we all learned in school about how things move and interact.
Well, the answer? Not even a fraction of a second. If classical physics were the whole truth, everything around us should literally collapse instantly. And figuring out exactly why that is leads us straight into some of the wildest discoveries in modern science. Let's dive right into Section 1, the classical physics paradox. To really wrap our heads around this, we kind of have to look back at how we initially tried to picture the atom and why that comforting mental image is fundamentally broken. For the longest time, following the famous Rutherford model, we all imagined atoms like a tiny little solar system, right? The positive nucleus is the sun, and the negative electrons are planets orbiting around it. But there's a fatal flaw here. Opposite electrical charges attract. And according to classical physics, moving charged particles have to radiate light and lose energy. So those orbiting electrons should inevitably spiral inward and just crash into the center, instantly destroying the atom.
Which brings us to Section 2, Niels Bohr's quantum solution. Since we aren't all just instantly vaporizing into thin air, classical physics absolutely had to be wrong here. And that introduces us to physicist Niels Bohr's radical, totally reality-bending solution.
Bohr proposed something that honestly seemed like magic at the time. He said that nature simply outright forbids the crash. Period. Instead of a free-roaming solar system, electrons are only allowed to exist on strict, specific, permitted orbits, and they're completely banned from the spaces in between. And while they're coasting on one of these permitted tracks, the electron safely moves without losing any energy at all. The theory commands it, and nature just obeys.
But we know atoms do eventually emit light. So how do they pull that off without constantly losing energy and crashing? Well, they do it using a quantum. A quantum is basically an indivisible packet or dose of energy. Think of it like an unbreakable piece of currency, like a coin that you simply cannot make change for. You can't spend half of it. You either spend the whole thing at once or not at all.
Now let's look at Section 3, Anatomy of the Quantum Leap. We're going to map out the incredibly strict, almost jagged rules of how atoms actually release that indivisible energy.
Here is exactly how a quantum leap goes down. When an atom absorbs energy, an electron gets bumped up to a higher permitted orbit. But it doesn't like being there. The atom wants stability. So it drops abruptly back down to a lower permitted orbit. And in that exact split second, it spits out the excess energy as that indivisible quantum of light.
But here is where things get really weird. Ask yourself this. When that electron moves from the upper orbit to the lower orbit, where is it while it's falling through the space in between?
The terrifying, logic-breaking answer is nowhere. It is literally nowhere. There is no trajectory. The journey just doesn't exist. There's only a beginning point and an end point, with the electron never, ever existing in the space between them.
Think about how wild that is compared to our everyday reality. In our normal, classical world, if an object falls, it's a continuous process, right? You can track and measure the middle of the fall. But a quantum leap? It's totally stripped of space and time. It's an instantaneous teleportation. One moment it's here, and instantly it's there, with absolutely zero spatial transition.
And we aren't just making wild guesses here. We know this is an absolute fact. When we look at atomic spectra, we see these solid, bright lines separated by total darkness. That bright line is the exact flash of a quantum being emitted. And that total blackness right next to it, that is hard, undeniable proof that there is no smooth, continuous transition. Falling simply does not exist at the atomic level.
Moving on to Section 4, why famous physicists panicked. Honestly, if this lack of a physical trajectory completely shatters your intuition and sounds like absolute nonsense, don't worry, you are in very good company.
Some of the greatest minds of the 20th century were legitimately horrified by this stuff. Take theoretical physicist Wolfgang Pauli. He was so incredibly frustrated by this total lack of logic that he famously wished he could just quit science entirely, become a movie comedian, and literally never hear about physics again.
Even Albert Einstein, a guy synonymous with genius, hated this unpredictability. He despised the idea so much that he openly compared himself to an ostrich, saying he'd rather hide his head in the sand of his own relativity theories just to avoid facing these, as he called them, nasty quantum leaps.
Then you've got Erwin Schrödinger. He's one of the brilliant founding fathers who actually helped build quantum theory in the first place, but he bitterly regretted ever dealing with those damned quantum jumps. He created the math for it, sure, but he absolutely hated the reality it pointed to.
And Niels Bohr, the guy who proposed the permitted orbits in the first place, basically just threw his hands up and concluded that the reality of the atom was so seriously bizarre, you just have to treat it with a sense of humor. You literally cannot apply human common sense to it.
And that takes us to our final part, Section 5, the unimaginable micro-world. Let's see how this all builds into an undeniable reality that we just have to accept, even if our brains are hardwired to reject it.
Here's the real crux of the problem. In our macro world, if you want to calculate a path, you need to know an object's exact speed and its exact position. But an electron is so unfathomably small that it lacks those simultaneous traits. They aren't just tiny little physical balls rolling around on tracks. They behave as both a particle of matter and a wave, meaning they can literally be in two places at the exact same time.
Because an electron is a particle and a wave simultaneously, trying to visually imagine the atom using everyday logic, it's fundamentally impossible. Our brains evolved to understand, throwing a rock, not teleporting matter. We can only truly understand and map the microworld through the pure, abstract language of mathematics. Niels Bohr actually hit the nail on the head when he said that if you aren't dizzy after your first encounter with quantum theory, you haven't understood a single word of it. It's supposed to feel dizzying because it breaks literally every rule we thought we knew.
So that leaves us with this final, kind of profound thought for this explainer. Every single object you interact with, the chair you're sitting in, the screen you're staring at right now, is made of these atoms. If the very foundation of our entire universe operates on rules that are utterly impossible to picture, what does that say about the reality we think we see every single day? Thanks for joining me on this explainer, and I really hope this leaves you seeing your world just a little bit differently today.